Good evening, all of you. So let us continue the balance of the lesson waves, and we are discussing with the principle of superposition of waves, in which one effect we have discussed, that is interference of waves, which is of two types, constructive and destructive interference. Now the second one is stationary waves. So listen here. In stationary waves, or how these stationary waves are formed. When two identical waves of same amplitude and frequency traveling in opposite directions with the same speed along the same path superpose each other, the resultant wave does not travel in either direction. Okay. So in stationary waves, or the stationary waves are formed when two identical waves of same amplitude and frequency, two waves having same amplitude and frequency, when they travel in opposite directions with the same speed along the same path, they superpose each other. The morning session we have seen interference is because of the superposition of two waves which are traveling in the same direction, right? But here the two waves are traveling in the opposite direction. They are also having same amplitude, same frequency, same speed, everything. And here when two waves superpose, you will get a form like this. Okay, so two waves when superpose, you will get a form like this. Understood? Here you can see in some places you are getting maximum value and some places we are getting very minimum value. So we can call the positions, that is, this is one of the position having maximum displacement or having which suffer, the particles suffer maximum displacement, but these are the points where the particles of the medium remain permanently at rest. Understood? So these points we call it as nodes. These are all nodes and these are the antinodes. Understood? Nodes and antinodes. Nodes means what? Nodes means the particles of the medium remain permanently at rest at this position, because one wave is coming in this way, another wave coming in this way, they will superpose and we will get the points like this, in which the nodes are the position or the points at which the particles of that medium remain permanently at rest. They have zero displacement, but these are the points of what? Maximum displacement, which we call as antinodes. The position of these nodes and antinodes do not change with time. That is why these waves are known as stationary waves, or also you can call as standing waves. Understood? So you know traveling wave. Traveling wave means it travels through a medium with a definite speed, and they transfer energy also, isn't it? Even though they do not transfer or do not move the material itself, it will transfer energy from one point to another. But in the case of this particular stationary wave or standing wave, there is no transfer of energy along the medium in either direction, neither towards positive side or towards negative side. There is no such transfer of energy, because they are simply standing waves. Understood? They are stationary waves which consist of nodes and antinodes. Clear for you? So there are two types of stationary waves, like transverse stationary waves and longitudinal stationary waves. Transverse, and second one is longitudinal stationary waves. So when two identical transverse waves traveling in opposite directions overlap, you will get a transverse standing wave. And when two identical longitudinal waves traveling in opposite directions overlap, a longitudinal stationary wave is formed. Okay, so that's all about stationary waves. And now we will move to the third part, that is the morning session we have told that it is beats. Beats. So the third one is beats, and the periodic variations in the intensity of sound caused by the superposition of two sound waves of slightly different frequencies. So beats means something related to sound. Okay, the periodic variations in the intensity of sound caused by the superposition of two sound waves of slightly different frequencies. So here the point is the waves of different frequencies. So when two sound waves of slightly different frequencies traveling along the same path in the same direction. Okay, so this is the first wave, you can suppose. Now another wave again. So both are of different frequencies. They are traveling along the same path in the same direction in a medium. They will superpose on each other. Okay, so intensity of the resultant sound at any point in the medium, it rises and falls alternately with time. And one rise and one fall of frequency, of intensity, not frequency, one rise and one fall of intensity constitute one beat. Understood? So you can say that the number of beats produced per second, the number of beats produced per second can be called as beat frequency. Clear? Number of beats produced per second is known as beat frequency. Okay. So beat frequency means difference in frequencies of the two superposing waves, because one may be of higher frequency, another may be of lower frequency. So surely there will be a difference in frequency, and that difference you will call as beat frequency. So the expression is nu beat is equal to nu 1 minus nu 2. Nu beat is equal to nu 1 minus nu 2. Understood? So that's all about beats. And the practical applications of beats may be, for tuning musical instruments. Musicians can use this beat phenomenon in tuning their musical instruments. Okay, so if an instrument is sounded against a standard frequency and tuned until the beats disappear, then the instrument is in tune with standard frequency. Understood? Also for producing colorful effects in music, these beats are used. It is also used in electronics for making low frequency oscillators. Okay, so these are the applications, practical applications of beats. So these all come under the principle of superposition of waves. Okay. So now we'll discuss the speed of a transverse wave. We have seen the speed of a traveling wave. Now speed of a transverse wave and longitudinal wave. First one is transverse wave. So here we are using the dimensional analysis, application of dimensional analysis to find the relation or to find the formula for the speed of transverse waves. Two cases we are considering. First one on a stretched string. Okay, and the second case is in a solid. For these two cases you have to find the speed of a transverse wave. So normally we will say that these physical quantities will depend upon these quantities. It is directly proportional to these quantities. Likewise, we will start the equation and finally we frame the equation by using the application of dimensional analysis. So here the wave velocity through a medium depends on the inertial and elastic properties. So you can say that the speed of a transverse wave through a stretched string is determined by two factors. First one is tension, T, force. Okay, tension means force. It is a measure of elasticity in the string. That is, without tension, no disturbance can propagate in the string. Understood? So tension in a string is a measure of elasticity in the string. Without tension, no disturbance can propagate in the string. So first of all, you have to write the dimension for this tension, which is equivalent to the dimension for force. And you all know the dimension for force, that is MLT raised to minus 2. Okay. Now the second one is, this speed of the transverse wave on a stretched string depends upon linear mass density. Linear mass density, which means mass per unit length. Mass per unit length. Clear? And it can be represented by the letter M. M, which means M by L. Okay. And so the dimension of M is M divided by L, or ML raised to minus 1. Understood? Now if you are taking the ratio of this tension to mass per unit length, you will get T by M, which is MLT raised to minus 2 divided by ML raised to minus 1. Okay, that is L squared T raised to minus 2. This is the dimension for the ratio T by M. So T by M is equal to L square T raised to minus 2. Now you know the speed has a dimension LT raised to minus 1, isn't it? So we can express V in terms of T and M. How? That is, V is equal to C into root of T by M. Okay, so from detailed mathematical analysis, it is found that this ratio C is equal to 1, and hence the speed of transverse waves on a stretched string is given by V is equal to root of T by M. So this is the expression for velocity of what? Velocity of a transverse wave in a stretched string. Understood? Now the second case is the speed of transverse wave in a solid, and here in the case of solid you have to take the factors like first one is elasticity. Solids, you have studied elasticity, or you can say the modulus of rigidity. Okay, now the second one is mass per unit volume. Mass per unit volume, or what is mass per unit volume? As it is density. Understood? Which determines its inertia. So two cases. For all the cases we are speaking about both inertial as well as elastic properties. So elastic property is represented by eta, and here this density determines the inertia. Inertia property. Okay. Here also you have to find the dimensions for eta as well as rho, and take the ratio for eta by rho, and the coefficient of coefficient of elasticity, that is rigidity, you will get the dimension as ML raised to minus 1 T raised to minus 2 divided by density has the dimension ML raised to minus 3. So you will get an answer L square T raised to minus 1. Understood? So LT raised to minus 1, again it is velocity. So L square T raised to minus 2 is what? V squared, right? So in order to find V, you will get root of eta by rho. Here also you can mark a constant which we don't know. And finally, this dimensionless constant is found to be unity. So the value is 1, that is V is equal to root of eta by rho. So two equations you got, that is V is equal to root of T by M, or this is for a stretched string. Okay, now the second, this is for string, and the second one is V equal to root of eta by rho, which is the case for a solid. So these are the expressions for speed of a transverse wave in a stretched string as well as in a solid. Okay. So next is speed of a longitudinal wave. Speed of a longitudinal wave. In this case also you have to find the speed in a liquid or a gas, then in a solid, like that. Okay. So for liquid or a gas, we can say that the speed of longitudinal wave through a fluid can be determined by two factors. First one is volume elasticity, okay, or you can call it as bulk modulus, K. Now the second one is density of the fluid. So in the previous method what we have discussed, the same thing you can follow here also. So here also we are taking the ratio of this K dimensions, okay, ratio of dimensions of K and density rho, and you will get m L raised to minus 1 T raised to 2 divided by m L raised to minus 3. This is the dimension for K and rho, and you will get the answer as L square T raised to minus 2. L T raised to minus 1, the whole raised to 2 is L square T raised to minus 2, which means it is velocity square, right? So you can say that V is equal to root of K by rho. So this is the expression for what? Longitudinal speed of longitudinal wave through a fluid. It only depends upon the bulk modulus and density. Understood? Also the speed of a longitudinal wave in a solid, after finding you will get the expression for solid. It is V is equal to root of K plus 4 by 3 eta divided by rho. K plus 4 by 3 eta divided by rho. Understood? Where K is the bulk modulus, eta is the modulus of rigidity, and rho is the density. This is the case of speed of longitudinal wave in a solid. Okay. So with this we are concluding this lesson. So that's all for your exams. So study all the lessons. All the lessons are there for your annual exam from both part 1 and part 2, except one lesson, that is kinetic theory of gases. Okay, so you all have to study well, prepare well for the exams, write your exams neatly. Okay, and all the best to all of you. Thank you.